Okay, the last section in Chapter 2, a discussion about energy. We're going to start it here, and we'll end up finishing this topic when we finally get to enzymes in the next chapter. So right now we're going to give it just a introductory idea from the point of thinking about creating and breaking chemical bonds. Before we start talking about the chemical energy, though, remember from physics, I bet, and other years, there's kinetic energy, the energy of motion. We'll be talking about that as we go along. We talk about molecules moving. We've already discussed it with hydrogen bonds. You guys remember all those heat equations you did in chemistry? Heat is thermal energy. It's associated with the kinetic energy when molecules are moving. You all know about potential energy. It's like maybe the child on the top of a slide has potential energy before it goes down. And then lastly, the one that we're going to focus on right now is chemical energy. And that's the energy available when you are going to break a bond, perhaps, in a chemical reaction. So, again, we can think about all these different types of energy. This boy here in the picture has potential energy. He dives off, he goes down. He's got kinetic energy, he's moving. He's going from a higher level to a lower level. You could also think about molecules diffusing. So think about, I like to think about maybe perfume molecules when somebody enters a room are concentrated when that person starts out there, and then they diffuse away. That's another form of losing energy. And then lastly, the one that we want to focus on now is chemical energy. This is basically a space-filling molecule of a glucose molecule, which we're going to rip apart in later chapters when we talk about glycolysis. But basically you can rip apart that glucose molecule into these different components. Just going back to here, always remember that every bond between two atoms has potential energy or potential chemical energy. There's two kinds of metabolism in our bodies, and you could think about those when we continue to talk about digestion later on and just how a system in a body works. Anabolic reactions are the building ones. I often like to think about anabolic steroids. They're the building and muscle building idea. But anabolic reactions are linking simple monomers together, like we've talked about with the carbohydrates or the building blocks of lipids. You need energy to make those bonds, and that energy gets captured in those bonds. When we eat food, very specifically, we're talking about humans, catabolic reactions break the bonds in those chemical molecules and release that energy. Oftentimes you're going to couple breaking those bonds and capturing that energy to something else that might transport the energy to another place. So this all brings up the idea of what happens to energy. Actually, before we get there, let's talk about two different kinds of energy changes. An endergonic means that you increase the free energy of the system. You might remember endothermic from chemistry. That was heat. We'll talk about heat in a minute, but right now I want to talk about free energy, which is designated by a G, or delta G, we're going to talk about in a minute. Free energy is energy available to do work in a system. If we take some reactants and take them to a new place and put them into products, and this would probably be an anabolic reaction. We're taking pieces and we're putting them together into a more complex molecule. It takes energy over time. On the flip side, if maybe this is a catabolic pathway, our free energy is released because you go from a higher state of energy to a lower state of energy, and you actually release that amount of energy. Now this could be breaking apart a glucose molecule to release energy for a reaction. Oh, should have looked at these. These are the close-up version. So again, exergonic means releasing energy. So free energy is G. It's on this scale. Time course of your reaction is down here. If your reactants go to a lower energy level, that energy has to go somewhere, and we're saying that it's released. Another way to look at it, again, exergonic is releasing the energy. Reactants started up here. Products ended down here. We're going to have a delta G that is less than 0 because we're going from a higher number that could have been maybe 50, going down to a 20. That means we're releasing 30. On the flip side, remember this is opposite what we saw before. Endergonic means you're putting energy into the system. You're starting out at this level. Again, let's call that 20. And you're getting up to this level. Maybe you're building a glucose molecule. You're going to get up to 50. You need 30 kcals per mole would probably be the units of energy to get there. Just another diagram to look at. So this always brings up a discussion about the laws of thermodynamics, which you may not have heard in your other classes. The first law of thermodynamics is that the total amount of energy before transformation equals the total amount after. Energy is never created or lost. Remember, it just transforms. So when we think about it in terms, this is the one that we want to think about mostly as far as life in the cell, is thinking about that second law of thermodynamics. A lot of times the energy before is not always recoverable to do work. So free energy is the energy available to do work. So sometimes there's energy that's not available to do work anymore. And that's when we can introduce this term called entropy. So this is the free energy equation. I couldn't get a delta up, so assume this is a delta. So the change in free energy is equal to the change in the enthalpy, or the heat in the system. And then you lose a loss of energy to a temperature change, and then to a change in entropy. Entropy is a measure of disorder. I kind of like to think about it as maybe as your room, or at least my children's rooms, that it could be nice and clean beginning of the week maybe, and by the end of the week entropy is taken over. Clothes don't get put back if they get tried on, and stuff just ends up everywhere. It's very easy to get to increased entropy. It takes a lot of energy, so actually it's harder. You put in energy to create order. So building things requires a lot of energy. Ripping things apart releases energy. And then you can also think about closed and open systems. So the Earth is pretty much an open system, right? We are taking energy in from the sun, and we are doing things on the planet, and things radiate away. But sometimes there's going to be a closed system, and that this disorder is always going to increase to a point where you can't go anymore. We'll talk about that in class. And then again, remember, this is just sort of a simplified discussion of energy. We're going to talk more when we get to enzymes later. But a lot of the reactions that we've taken a look at or gotten ready to talk about are here. So if you break apart a sucrose molecule and add in some water and have an enzyme there to help you out, there's a change in delta G of 7. And in class we'll talk about whether you think that's a positive or a negative. And then triglycerides, the attachments that are to glycerol to make a fat, glycerol plus a fatty acid makes a monoglyceride. That has a delta G of 3.5. And then again, we'll discuss whether that's a plus or a minus in class. And lastly, we'll talk about photosynthesis later on, but you certainly know, hopefully from middle school science, that plants take in carbon dioxide, they use the energy from the sun and water, and they make glucose and oxygen for us to breathe. And that, again, the delta G is 686. And we'll go talk about it in class as to whether that's a plus or a minus. Okay, bye.